So as I shared with you earlier, okay, there is no there is some values that you can get from table B8. Okay, so for nitrogen there is values that you can get from table B8, so that you can get the enthalpy value, and then use straight away nitrogen as your reference state at 25 degrees Celsius and 5 atm. But for acetone there is no tabulated value, so we need to choose one stream condition as the reference state. In this example, we pick acetone liquid at 25 degrees Celsius 5 atm as its reference state. So this is where actually we construct the inlet outlet table. Okay, so for example, like in this particular case, we have acetone in vapor, acetone in liquid, as well as nitrogen. So these are the components that we have in our condenser. What is coming in is actually there is a vapor, that is acetone vapor, as well as nitrogen that is coming in. So you know that from the when you do the material balance, we know that the acetone vapor that is coming in is at 66.9, and we do not know what will be the specific internal energy yet here. And we also know that there is nitrogen that is coming in at 33.1 with another value of specific enthalpy. But in your, okay, if let's say we draw back this, so this is only acetone which is in vapor as well as nitrogen. So because there is no acetone in liquid coming in together, so we just leave this value blank. So we just put 0 and 0. And then what is going out from here? So you have two streams that is going out. One is acetone in vapor, okay? And then there is a value of delta H3. And then there is another one which is acetone in liquid. And then you also have the, what do you call that? The nitrogen that is going out. Okay, nitrogen which is not affected, but actually there is a change of temperature from 65 now become 20 degrees Celsius. Okay, then it exit the same stream as the acetone in vapor, so you value it as H4. So why do we put the value of acetone in liquid as 0? Okay, there's something that you have to figure out, that initially in the previous slide that we have decided that acetone, which is at liquid, 25 degrees Celsius and 5 atm, becomes our reference state. So when it becomes our reference state, straight away the enthalpy value at that particular point is reset as 0. Okay, so we have 63.55 as the value of the number of mole out of acetone in liquid, but because this is chosen, okay, the state here 20 degrees Celsius and 5 atm is chosen as the reference state for acetone process. So straight away this enthalpy, specific enthalpy, is equals to 0. So this is where actually we construct the inlet outlet enthalpy table. Okay. What we can do here, if we look at the notes, nitrogen has one inlet gas which is at 65 degrees Celsius 1 atm, which is from this particular stream. And then it have one outlet stage which is at the top here. Nitrogen goes to the top, but now the temperature and pressure change from 65 to 20 and 1 atm to 5 atm. Acetone has one inlet. Okay, it comes as vapor at 65 degrees Celsius 5 atm, but then it has two outlets. One it goes as vapor, another one goes as liquid. So we have to pick one stream so that we can actually have our reference state for acetone. And now we pick the stream of the acetone liquid in the bottom stream, okay, at 20 degrees Celsius 5 atm as our reference state. So now that is why we reset the value of enthalpy here as 0. But there is a but here. You can also choose the acetone at the inlet which has a vapor of 65 degrees Celsius 5 atm as your reference point. if you pick that value as your reference point, okay, which is at 65 degrees Celsius 580 m, then you can set the section here this as 0, but you have some value that you have to specify here. This is no longer 0. And if let's say you decided that, okay, I want to make the acetone in vapor at 20 degrees Celsius 580 m as the reference state, so instead of your specified H3 here, this is where actually you put 0. So again, it is up to you which particular state that you want to choose to become your reference state. Okay, it's up to you and entirely up to you. But it's just easier for you to pick one stream, okay, and set it as reference state. So ultimately, that value of the enthalpy for that state is equals to 0. Okay. So when we construct the inlet outlet table, okay, so this is the value that we got again. So we didn't we are actually constructing this particular table, and then we want to fill up what will be the hypothetical process change from one step to another step. So let's look at the acetone itself. So when we pick acetone has 20 degrees Celsius 580 m liquid as its reference state. Okay, so we need to imagine that how does from 20 degrees Celsius 580 m liquid would become 65 degrees Celsius vapor in 180 m. Okay, or we also need to figure out that how does 20 degrees Celsius 580 m liquid would become 20 degrees Celsius 580 m in vapor. So because those are the things that we need to list out in our hypothetical process part. In this case, let's figure out that how does from 65 degrees Celsius vapor in 180 m would finally become 20 degrees Celsius 580 m in liquid. So what's the process that it gone through? Okay, so you imagine that it works the other way around. We want to make sure that 20 degrees Celsius 580 m in liquid to become 65 degrees Celsius vapor in 180 m. So the process that it goes through here is actually it has some changes, okay, from it has some changes in terms of the temperature itself. Sorry, the pressure. For example, like 20 degrees Celsius 580 m, it changed the pressure to 180 m, okay, at fixed temperature and fixed state, which is in liquid as well. And after that, there is a change of temperature, which is at 180 m and liquid form from 20 degree to 56 degree. Why is it 56 degree? Because if you refer to table B1, okay, you will get to know that the boiling point for the acetone is at 56 degrees Celsius. So at 56 degrees Celsius, there is change of temperature, okay, and then from here from 56 degrees Celsius there is a change of phase, which is the heat, the boiling temperature. So there is a change of phase from liquid to become vapor, so there is another one. And then there is also another change, which is change of temperature from 56 degrees Celsius to become 65 degrees Celsius. So if we refer back to the initial table, okay, we want to fill up this value, okay, and then this value delta H1. So in order for us to calculate the delta H1, it is equivalent to, okay, delta H1A, which is here, plus delta H1B, which is here, plus delta H1C, which is at this point, plus delta H1D, which is at this point. So only then, if let's say we calculate all of this, then we'll be able to fill up what will be the delta H1 value that we can put in this particular table. Okay. Um, so how do we calculate that? Alright. So this is I have explained to you earlier. So how do we determine, because we have this as our reference state, okay, and then we want to make sure that it changes here. So you have to imagine this is not 25 degree, this is supposed to be 20 degree. So how do we calculate here? right? In order for us to, okay, this is supposed to be delta H. Pressure is reduced from 5 atm to 1 atm. So we can use the equation of delta H equals to specific volume multiplied with delta P. We can get the specific gravity from table B1. Specific gravity from table B1, which is given at 791 gram per liter. And we know that the molecular mass, okay, for acetone is 58.08. So we can determine that specific volume is actually m divided by the specific gravity here, where you can get it is at actually equals to 0.00734 L per mole. So if you multiply with the changes of pressure, okay, 0.0734 multiply with the change of 5 to 1, okay, 5 minus 1 atm, then you'll be able to determine what will be your delta H value. Okay, so the process of, this is the hypothetical process that is happening from 20 degrees Celsius to 65 degrees Celsius. So you have a change of pressure initially at similar temperature and similar phase, and then there is a change of temperature. So this is actually delta H1B, and then there is a change of from here, which is the change of temperature, change of phase, which is from liquid, now it become vapor. And then after that, there is another change of temperature from 56 to 65 degrees Celsius. So when you total it up, then you need to know that this is how actually you put the value, the enthalpy changes. Okay, when she's, you just add up all these enthalpy changes, delta H1A plus delta H1B and so on. And then you substitute the information here. Delta H1A, you know that it is equivalent to V delta P. So this is where actually you put V delta P. And then plus with the changes, okay, from 20 degree to 56 degree CP So this is where actually, because there is a change of enthalpy in terms of temperature from 20 to 56 degrees Celsius. Okay. Why it is 56? Why we stop at 56, not straight away to 65? Because from 56 to 65 already there is a change of phase. So we need to split it out. So we use the CPDT for acetone. So where do we get the value for CPDT? This is where actually you can revisit table B4, okay, where you can get the value for A, B, and C, and you can substitute in it, in this. Then you can actually determine from 20 degree to 56 degree, as what we have done in the previous example. You can actually calculate those things and you can substitute it here. And you can get the latent heat of vaporization of acetone, which is also, you can get this value from table B1. And you can also further recalculate the change of uh, the enthalpy change by calculate the CPDT of acetone in vapor from 56 to 65. And then you'll be able to substitute inside here. Then only then you'll be able to determine the delta H1 that you can include in this table.